Next section is separable of variables method for solving PDE. In many situations, more than 2 variables, 3 or 4 variables. In particular, those equations that involve the Laplacian operator in 3-dimensional space. So, and depends on the geometry of your problem. It means either the initial condition or the boundary condition, or you might want to use a different coordinate system. So, most generally, you can use Cartesian coordinates, cylindrical coordinate, or spherical coordinates. So that's the 3 that commonly used. And we can do separation of variable on all 3 of them. And the consequence of using different coordinate systems is the equation for different different factor in your solution becomes different. And many of those are the ODE that we talked about in the last chapter, so like the gender equation, Bessel equation, and so on. And so that's why those equations are useful, because once we do a separation where we actually get to see those equations again. All right, so let's do the Cartesian one is, we can consider that first, and that is actually quite straightforward. But as an illustration, we can start with that first. So the equation we can do you can illustrate with a Laplace equation, but more generally, you can add the constant term, not a constant, linear term, and that becomes a Helmholtz equation. So if you have this Laplacian, if Laplacian side is 0, that's called the Laplace equation. But in this case, we have Laplacian plus k squared equals to 0. Right, and we can treat k squared as positive. That's why we write it as k squared. That's the usual example in Helmholtz equation. For negative value, I mean, it's still a valid equation. The form of the solution will be a little different. But to illustrate just separation of variable, we'll just use this form, using a positive k squared. The k is a parameter. K squared is this real positive parameter. Okay, and in Cartesian coordinate, Laplacian is straightforward. So it becomes a partial side, partial square side, partial x squared. Side, partial y squared, partial square side, partial c squared. And then finally, you have this k squared side term equals to 0. All right, the idea of separation variable is to find one solution that psi is equals to 3 factor that function of the respective coordinate variable. So that's like the first factor depends on x, we call it the capital X. And then the function capital Y depends on Y. Capital Z depends on Z. Right? And that obviously not all solutions will be factorized like that. But that because this is a linear equation, later on we just combine different separable solutions. So the most general one will be a sum over all this term. Right? The sum of overall separable solution is still a solution, but the derived equation for each factor, we just consider one of them. So we don't need to do the sum now, but once we figure out what the equation or the solution for each factor, then we just sum over all possible solutions, and that generally give you a general solution, right? And it means that we can find all solution in separable form, but not separable in just single term. You just sum over sometimes infinite many of these separable solution, right? Then for this one, what you do is just substitute this in the equation, and the first term operates just on x, right? The second term operates just on y, the capital Y. The third term operates just on the third factor z, capital Z, right? And then you can just write the first one is y times z, and because it now depends on just one variable, it becomes a total derivative, d squared capital X dx squared, and then plus x times z, d squared y, dy squared, plus x y, d squared z, d z squared. I mean, sometimes in handwriting, it's a little bit difficult. You need to distinguish the capital and the lowercase one, but just need to be a little careful, right? And the next step is divide the whole thing by the same function, and you might actually ask that whether that is always possible, because if the function becomes zero, then obviously divided by zero is not a very good way to do it. But the idea is that this is like a process. This just one step in the derivation, we kind of doing something slightly illegally, or not considering whether it's legal or not, and finally get a solution first, and then finally we check going back to this step to see before you take the divided by this function, and show that the solution that we get in this process actually satisfies this equation without taking the division. So then we don't need to worry about divided by zero issue. Okay, so that's the idea. So we do that in order to get the equation that we want, but finally we check that the solution that we get actually satisfies back the equation, or you can plug it back to here and show that the solution you get is actually a solution for this one. Okay, so that's just a mathematical subtlety. So the idea why we do that is we divide the whole thing by this psi function. So so the psi in the denominator, which is x times y times z. Now for the first term, you cancel y and z. So leave it like 1 over x, capital X, x dx squared, right? And then the second term becomes 1 over y, y squared. The third term is 1 over z. I forgot the k squared, x, y, z. Forgot the Helmholtz equation has a linear term, d squared. D squared c, d z squared. And finally, the Helmholtz equation becomes just a constant. Okay. Now the argument in the next step is that now you have different terms that depends on different variables. So the first term depends on x. This is a function of x. The first term is a function of x only. The second term is a function of y only. Second term is a function of z only. The last term is just a constant, so it doesn't matter. What the argument is that x, y, z, for your function, you define your domain that you try to solve, and that generally involve a volume. And for all the point, x, y, z point in the volume, you need to satisfy this equation. And you can just iteratively argue that in order to have that property, or for all points within the volume, you satisfy this equation, that would require that each of these terms are constant. So this is a constant, this is a constant, this is a constant. They might be different constant, but at least they must be constant. You know this. Then you have 4 constant now add up to 0. Is that okay? So so that's the argument. So now we just need to assign the variable for this constant. I think just for your textbook, this, and we call this minus L squared. Now, whether it's positive or negative, undetermined at this stage. We just write a negative L squared. It looks like a negative, but it doesn't have to be negative. You can require L squared to be negative, so that becomes a positive term. All right, so that actually is just like we arbitrarily assign notation first, but whether it's positive or negative depends on the situation. And then the next one, I think the textbook called minus M squared, and this one called minus N squared. Likewise, these may not be positive or negative. And then you have a K squared. Right. So minus L squared minus M squared minus N squared plus K squared equals 0. So that's a requirement for all these constants. Is that okay? So as long as they add up to be 0, then that's fine. Now for this particular choice of K squared, if you choose K squared to be positive, then obviously you can choose both L squared, M squared, N squared as positive. That's one choice that is possible, but not necessary. So you can choose like one of them or 2 of them becomes positive. A negative, then this all 3 becomes positive, and there's only one negative, that is also valid. Right? It depends on the situation, depends on boundary condition and all that. Right? So it's still not totally fixed. Even if K squared is positive, then all these terms, as long as they are not all negative, if they are all, I mean, L squared, M squared, M squared, N squared are all negative, then this becomes all positive. All 4 terms positive, you cannot add to 0 unless they're all 0, right? And that's its trivial solution, right? And so once we assign the name, then we can just solve this equation. Just you have this equation to solve, and this equation to solve, and this equation to solve, right? And you know how to solve this equation, right? For Cartesian coordinate is very easy, so you just multiply x to the other side. Yes, d squared capital XD x squared equals to minus L squared terms. So what is the solution? Oh, other general solution. E, yeah, you can use exponential function e to the plus or minus L times x, right? I times L times x, right? That's one valid choice. So you can use exponential function or sine and cosine, because this is a simple harmonic oscillator. You use sine and cosine. Let's follow your textbook. The textbook write down the solution. No, your textbook didn't write. That's kind of strange. But anyway, let's just use our own notation. Just arbitrary constant A times cosine Lx. That's B times sine Lx. Right? That's one valid choice. Or if you don't like, you can use exponential function e to the I Lx. As long as the 2 solutions are independent solutions. Right. That assuming L squared is positive, and L is just a real number, right? And so these are the choice. If L squared is negative, so the whole thing is positive, then instead of cos and cosine and sine, you get cos and sinh, and this becomes exponential function. You know that all that, right? We solved this equation before. So that's the x1. And for the Cartesian coordinate, it's really straightforward. The y equation and z equation exactly of the same form. So all you need to do is just change L to either m and n. And then this is for the y and z solution. Obviously, change the coefficient, general coefficient. Is okay? So, and then finally you impose just this condition, k squared minus, or k squared equals the L squared plus m squared plus n squared. Right? And that will be a general solution. Okay, so then that's what just why at the bottom. So this general solution, general idea is psi is equal to sum over L, m, and n. That depends on your choice. That that can, okay. I mean, they may not be integer. It can be. It just as a saying a sum, but then it's just all possible value of L, m, and n. That can be many different situations because in some situation you have boundary condition that will restrict the choice of your L, m, n, like restricted to some integer and multiplied by some constant. So then you sum over integer, just sum over integer. In some situation, it might be a continuum. So all values are possible. Right? It depends on that. So the sum becomes an integration. And those are also possible. Right? And then you sum over your three factors, A, cosine, Lx, B, and Lx. So obviously, this coefficient all depends on LMN. LMN. And then C cosine M Y plus D sine M Y. And then E cosine NZ plus F NZ. Again, all the coefficients depends on your choice of LMN. Right? Now that is your general solution, right? With all these unknown to be specified coefficient, right? And then those are to be chosen to satisfy initial condition or boundary condition, right? Okay, so that's the general idea, and I should say the summations subject to the constraint k squared equals L squared plus m squared plus n squared. Okay, that's the idea. It's okay. So let's see how much time I have. About 10 minutes. We could either go to cylindrical or there's an example which is straightforward. This is to illustrate what we call the bound, how to impose the boundary condition. Okay, let's just do it before, because we don't have time to go to cylindrical coordinate now. So just as an illustration of this form of this solution, just consider this example in your textbook. So you have a box. So exactly the same equation. Is it the same or without a k? Just Laplace equation. So k basically setting k to 0. So for Laplace equation, k is 0. And now obviously one of these would be negative. L squared, m squared, n squared. One of that would be negative. And we can specify which one is positive, negative by the consider the boundary condition. X is the x, y, z. The origin is one corner. X is from 0 to whatever they call I mean, my coordinates is write a little differently. For your textbook code, x, y, both are c, 0 to c, 0 to c. Those that basically xy plane is a square, and then this is L. For z is 0 to L. And then what else? K is 0. And the boundary condition is that every surface is 0 except the top one, right? The zero. So this every surface is 0. 0, 1, 2, 3. The bottom and the side, 1, 2, 3, 4, 5. Right, all surfaces. This is the origin. Here. So all the 5 surfaces are 0. The top one called the value of the solution is V, right? Yeah, and they solve the Laplace equation with K is 0. Okay, so you have 5 minutes. So now we apply this solution. Now in the X solution, X you have to include the 2 surfaces that the value is 0, so it's easier to choose X solution so that at both X is 0 and X equals C, the X solution, the capital X solution is 0. And likewise, the Y solution also should be 0. And with your choice of the range of your variable 0 to C and 0 to C, then this 2 factor is easy to write down because you can we talk about that in Fourier series chapter already. So it's you have to unspecified sum first, and then the X solution will be like this one without the cosine term. We just keep the sine term, right? And sine of to satisfy the boundary condition, you want the you want when X equals to C, X equals to pi, so L pi X. X equals C L, so a sum of L from 1 to infinity. That you don't include 0 because 0 sine 0 is 0, right? But that gives you this solution, this term, and fixing the. Now I redefine the L because now this is not L squared, it's L squared pi squared divided by C squared, right? So I redefine this meaning of L. But that is fine. So that is the X factor, capital X factor. The capital Y factor is similar. Sine of m pi x, m pi y over C. The sum over m is 1 to infinity also. Is that okay? So you fix the X, capital Y factor. Now you have a capital Z factor. And now you cannot use that because that will set both to 0. But and then because of this is Laplace equation, K squared is 0. So both this term L squared, M squared, after you redefine it, this is positive. So you need to choose a N squared. The last term will becomes negative, right? So instead of cosine and sine, for negative N, you get a cos or sinh, right? So it's basically changing the sign of your equation. Now this becomes a positive sign, right? Then you get the solution cos or sin or exponential function. And for this particular case, because the lower boundary is 0, only the upper boundary is non-zero, so it's easier to use the sinh factor. Use the sinh factor to satisfy the equation. that in that case, you don't have to use pi because it's not a periodic solution, so you can use, let's see, just see what your textbook use. The C vector is, I think your textbook just use rho, see? Why you use rho? I don't know, or whatever. Well, instead of n, you can use as well use n actually. Use only your textbook using rho. So rho take this actually instead of n squared, rho squared. Right. Obviously, this would depend on your choice of L and M. Right. And okay. I guess that's it. And then you need to the condition is to be satisfied is that this ends becomes a minus rho square. So rho square equals to, after redefining this, is L pi over C square plus M pi over C square. You need to satisfy this one. Okay, 1 minute. So this form, I mean, you need a coefficient, whatever the coefficient, unknown coefficient A or whatever A. And this form already satisfies the 5, 0 boundary condition. One boundary condition left is the top one. So you just write the boundary condition at equals CL, right? You just write that that has a value of V. It's not a function, so make it a little easier. It equals the sum of L, sum of M, right? And then you have A, L, M, like get outside sine x over c sine n pi y, m pi y over c, and then sinh rho lm l. And rho lm is given by this one, so it depends on L and M. Okay, and that becomes a Fourier series expansion. It's actually a Fourier sine series, and we did that before. You know how to do it now because we went through the Fourier series chapter. We just use the formula for Fourier expansion that basically involving integrating V multiplied by the same factor sine and sine, and then multiply with the corresponding normalization constant, and you get your coefficient ALM times this one. So this times that becomes your coefficient, expansion coefficient. So this times that equals to whatever V and integrate V multiplied by these three, and multiplied by the normalization constant of your Fourier series. It's okay, and that formula is in your textbook. But anyway, that's the way to solve it. It's okay. So you know because I'm out of time, right? Okay. Any question about this process? So this actually is an easy one. You probably have seen it before, but we'll move on to other coordinate system next Monday.